Hello, welcome back to Math 155. This is lecture 14, and today we're going to be continuing to think about how we maximize or minimize functions, but rather than doing that over the whole domain of a function, we're going to be restricting ourselves to a particular curve. So what we mean by that is we have some constraint on our function. For example, this could be a path that we might take around a hillside, and we want to know what is the maximum point that we reach, what's the maximum height that we reach on that path that we take. So we're going to be talking about this in terms of something called constrained optimizations. That's some new terminology today, as well as things called Lagrange multipliers. And this method of Lagrange multipliers allows us to find the maxima or minima of a function when we are constrained to a particular curve. Okay, so let's dive in. Essentially, the problem is we have a function, f of x, y, and we want to find its maximum and minimum, and we could do that in general by finding its critical points. But what happens if we want to restrict that to a particular path? So if we've got this diagram down here on the left, where we have a function f of x, y shown by these level curves, and we want to find the maximum or minimum value, but we want to do it along this blue curve. So you can imagine this f of x, y is, say, just the height of a hillside, and each of these level curves is therefore a contour on that hillside, and the blue curve is a trajectory that you take. So you're walking along a path that goes up this hill, say, and then eventually comes down this hill. You want to know how high you reach. That's essentially the nature of this type of problem. So we can intuitively see what's going on here if we think about what happens as we cross a level curve. For example, if we think about this point here, we know that this can't be a maximum or minimum value. It can't be an extrema, because on this side of our level curve, our f value, f of x, y, is going to be less than 7. And on this side, it's going to be greater than 7. So we know that this can't be a maximum or minima whenever we are crossing a level curve. If we instead consider this point here, where our constraint function is tangent to a level curve, well, that means that here you're increasing your height, your f value, as you go in this direction, and then on the other side of it, we are decreasing. So intuitively, that should tell us that there is a maximum at some point between these two arrows. And we see here that where this blue dot is, that's just about where our constraint curve, our trajectory that we're taking, is just tangent to a level curve. So this is related to something called the method of Lagrange multipliers. And these allow us to find a maximum or minimum of a function subject to a condition. In this case, subject to this condition here, g of x, y is equal to k. By thinking about what happens with our gradient vectors. Okay, so if we think about our gradient of f, we know that our gradient of f, which say looks like this, so our grad of f, we know that this is perpendicular to level curves. That's what we've learned previously. But seeing as the constraint curve, our g, is also tangent to our level curve, that means that the gradient of g must also be perpendicular to the level curve. So we don't know which direction it's pointing in. It could point in the same direction as f. So this could be our grad g. Could look something like this, or it could also point in this direction. So this means that our gradient of our function, grad of f, is parallel or anti-parallel to the gradient of our function g at a particular point p. And that point p is going to be a local extrema. So it's either going to be a maximum or a minimum. So if we can visualize things sometimes like we do on the left, this is a way that we could just sort of intuitively work it out by examining this diagram, but we can also work it out mathematically by saying if we have a function f of x, y subject to this condition g of x, y is equal to k, then we can say that the grad of f at a point p is equal to lambda times the grad of g at that point p as well for some constant lambda. So this lambda could be positive or negative. If it's positive, then grad of G and grad of F are pointing in the same direction. If the lambda is negative, then they are pointing in opposite directions. And these values of lambda are just called Lagrange multipliers. So you don't really need to worry about anything else other than thinking about solving these conditions here. So this is really just a set of equations, right? So we know how to work out our grad of F or G. That's just our partial of F with respect to X, which is equal to lambda times by our partial of G with respect to X. And likewise, we have our partial with respect to Y of F is equal to lambda times our partial of G with respect to Y. And then we have this constraint, G of X, Y is equal to K. So essentially we have three equations here that we need to solve so that we can find X, Y, and lambda. So X and Y are going to be our point that our maxima or minima occurs at, and our lambda is going to be our Lagrange multiplier. So we can find all possible locations for our extrema using these functions by solving these equations here, and we can then use those values to calculate what the actual maximum or minimum value is. Okay, so let's consider an example here. So we've got some level curves given in here shown by these red curves with the blue numbers, which are showing the function values on those level curves. And we're asked to determine the minimum value of f of xy subject to this constraint g of xy is equal to 0. This g of xy is equal to 0 is shown by this level curve here. So this is just our g of xy is equal to 0. So we know from above that if we are crossing a level curve like we do here, or here, or here, so on, that we can't have a maximum or a minimum value because when we're on one side of the level curve, we know that we have a higher value than the level curve, and when we're on the other side, we have a lower value. But here, at this point P, we see that we have our constraint curve tangent to our level curve. And so this here is going to be a minimum. And we know it's a minimum because this value down here is 8. On this side here, we're above 8. On this side here, we're also above 8. And so this is a minimum value. We can therefore write that f has a minimum value of 8 when our inputs are restricted to curve g of xy is equal to 0. Okay, let's step through another example now. So here we're asked to find the maximum minimum values of this function p of xy. Doesn't matter that it's a p, just changed it out from being an f. So you've got p of xy is equal to x squared plus xy plus 2y squared minus y, but we want to do this subject to the constraint x squared plus 2y squared is equal to 3. So the first thing we can do is we can relabel this constraint as a g of xy is equal to x squared plus 2y squared minus 3. This gives us then our constraint that we want g of xy to be equal to 0. It just makes the notation a little bit easier. And then using our method of Lagrange multipliers, which I'm just going to abbreviate to MOLM here, we have that our gradient of our function p must be equal to lambda, Lagrange multiplier, times by the gradient of g, our constraint. So what do we do? Well, this is just looking at our partial derivatives of our function p. So p with respect to x has got to be equal to lambda times our partial of g with respect to x. So what's that? Well, we have 2x plus y must equal lambda times by 2x. Okay, we'll just leave that in that form for now. Okay, so with respect to y, we now have our partial of p is going to be equal to lambda times the partial of g with respect to y. So working this out, we're going to have x plus 4y minus 1 is going to equal lambda times by 4y. And then finally, we're also going to have our constraint. So we have x squared plus 2y squared is going to equal 3. Or minus 3 is equal to 0. These are the same things. Okay, so how do we solve this? Well, there isn't really a hard and fast rule in terms of how we do this. You've got three equations here. You've got this equation here, and this equation here, and you've got to go through a process of elimination to eliminate either your lambda x or y, and then work backwards and substitute values in to find the others. So for example, here, we can notice that on the right-hand side, we've got a 2, here we've got a 2 lambda x, and over here we've got a 4 lambda y. So we can do a little bit of manipulation to make these the right-hand side of these things equal to each other. So if we multiply this by 2y, then we're going to end up with 4xy plus 2y squared is going to equal 4 lambda xy. And if we multiply this one here by 2x, or actually just x in this case, multiply it by x, we're going to get x squared plus 4xy minus x is equal to 4 lambda xy. So note here that our right-hand sides of these functions are the same. That means that we can equate them and do some cancelling. So if we call this equation 1 and this equation 2, so we can eliminate our lambda by setting 1 equal to 2. So now we have 4xy plus 2y squared is going to equal x squared plus 4xy minus x. And notice here that our 4xy's will cancel. And we can do a little bit of rearranging as well. We could get these to the same side, but actually I'm just going to leave them in their same place. So let's just leave this as 2y squared is equal to x squared minus x. Okay, so from here, we now need to substitute this equation, which I'll just underline a different color here. Here we've got a 2y squared, and we've also got a 2y squared up here. So we can substitute this into this function up here, into our constraint. So if we do that, we're going to end up with x squared plus x squared minus x is equal to 3. And then if we expand this out, we're going to have 2x squared minus x minus 3 is equal to 0. And this happens to factorize into 2x minus 3, x times by x plus 1 is equal to 0. So this gives us that x is equal to 3 over 2, or x is equal to minus 1. So we now have two values here. So we can substitute these values in. So scroll down a little bit so there's a bit more space. If we think about what occurs when x is equal to 3 over 2, we can substitute this value here back into our equation here, okay? So this will give us our value of y. So we now have 2y squared is then equal to 9 over 4 minus 3 over 2. So that's 3 over 2 squared minus 3 over 2 is going to give us 2y squared is equal to 3 over 4. Or simply y is equal to plus or minus square root of 3 over 8. I'll squeeze it in on this slide as well. If we think about what happens when x is equal to minus 1, again, substituting this into this equation here, we end up with 2y squared is equal to 1 minus 1, which implies that y squared is equal to 1, or y is equal to plus or minus 1. So this means that we now have values for x, we have corresponding values for y, and that means that we can, we've identified all of our extrema. So if we scroll down here, this is this diagram on the right hand side is showing our function p of xy, and the green curve is our constraint. And we can see that these dots, these points here that have been identified, are the minima and maxima that we've just identified. We don't know whether they're minima or maxima yet, but we have here, for example, we've got the point minus 1, 1. And we have this point over here is going to be 3 over 2 root 3 over 8. This is all root 3 over 3/8 here. We've got this point down here, which is going to be 3/2 minus √3/8. Recall, all we're doing here is we're just using all 4 combinations of our x and y values here. So we can have 2 possible values of x, and that they each give us 2 possible values of y. And then here, we end up with this point being -1, -1. Okay, so we can summarize this in a table. If we write down our x, y values and our corresponding f of x, y values, so just substituting those in. So these are our points that we've identified where we have a local extrema. And we can see all of these are going to be local extrema because all of these points that I've just identified in the diagram on the right-hand side are all tangent to our level curves. So here we are tangent to our level curve. We're approaching it from above, just about touching it, and then moving away from it. So this automatically tells me that this is going to be a minimum, and we see that this minimum occurs for a value of 1. So this here is a value of 1. So I can draw that in there. -1, 1 is going to be a value of 1, and that's going to be a minimum. If we think about some of these other points, if we carry on going in an anti-clockwise direction, this one down here, we approach from below, and we just about touch our level curve equal to, in this case, 5. So it's a little bit difficult to trace around, but it's 5 there. You can also see it just about there. So this is a function value of 5. We're approaching it from below, and then we leave it from below as well. So this is going to be a maximum, and this occurs at a value of 5. So this here is maximum of 5. If we do the same process for these other points over here, we see that this one turns out to be a local minimum, and this one here is going to be a local maximum. The function values here, if you plug them into the function, we end up with 3 minus ½ of √3/8, which is approximately 2.69, and the other one is 3 plus ½ of √3/8, which is approximately 3.31. We can also see that this level curve here in the bottom left, where we have this maximum, is clearly higher than both of the other 2 values on the right hand side, the local minimum and local maximum. So we see that this here is actually an absolute maximum, and this one up here, -1, 1, is an absolute minimum. Okay, that's it for today's lecture. Make sure you're familiar with these new terminologies of constrained optimization and Lagrange multipliers, and I'll see you in the problem class. Thanks.